Hello, this is Dr. Christy Lukes, your instructor for Chemical Engineering 3111. We are looking now at Lab 4, which the topics are numerical calculus, so differentiation and integration. First, we looked at differentiation, and for this there were just lots and lots of formulas. And this is the sort of thing that you'll look them up when you need them. There were 3 different types of formulas. The first were forward differences, next backward differences, and central differences. And to use these, it depended on whether or not you were, say, at the first point in a data set, you would need to use a forward difference. At the tail end of a data set, you would use the backward differences. And for points in between, you could use any of these. Now, the idea is that you get different precision, so order delta x. And basically, the higher precision, regardless of whether delta x is greater than 1 or less than 1. But the idea is that the higher precision is going to be based on using a higher delta x. So delta x squared is better than a delta x to the 4th better than a delta x squared. And so this gets you more and more precise answers, and it's a matter of just simply looking up the correct formula and applying it. For this course, what I really recommend you do is set up a formula that points to data and then have that, do that for a random data set. But that allows you to then copy and paste those formulas, and you can do this for all of the various formulas, and then you have them ready to go. Next, we looked at integration, and here we had 2 techniques we looked at. We looked at the trapezoid rule and Simpson's rule. And both of these you should have covered in a calculus course. Now, the trapezoid rule is the more versatile of the functions because it can be used if the intervals are regular or irregular, which means that is the spacing even or, varied. That means it's going to work for most experimental data and so forth. Now, there is a shortcut formula that you can use, but that's only going to work if you have regular intervals. Simpson's rule requires that you have evenly spaced data or regular intervals. Also, you must have an even number of subintervals, which means you need to have an odd number of data points. And that's going to be very important. Now, Simpson's rule is going to be the more precise, so when it's possible to use Simpson's rule, that will get you the better quality answer. But trapezoid rule is going to be more generally more versatile and generally appropriate. So why on earth would you need this? Well, this is from separations. Absorption formulas, one of the ways that you can do this, this is an absorption tower here where you have a gas and a liquid, you're bringing them together, so you're going to spray a liquid from the top, have a gas enter from the bottom, and they're going to go over packing, which will disperse the 2 fluids so that they will come into contact with each other. And where they have contact, you'll have an interface between the gas and the liquid. And mass transfer happens at that point. Now, the purpose of an absorption or stripping tower such as this is to clean either the liquid phase or the gas phase of a contaminant or some undesired chemical, or it can be used to actually transfer material into the other substance. But it's all about mass transfer. To design something like this, there are many, many ways of doing it, but here is a sampling of some of the common formulas that are used. Essentially what you do is you take the height of a transfer unit and multiply it by the number of transfer units. And depending on the data, the driving force, exactly what it is you're trying to get out of the system, you have a variety of different formulas for these. And so you would choose a particular driving force and set a variable. So this is gas phase composition, and then that determines your formulas. But what you'll notice is the formulas here are all involving integrals. So integrals, they're complicated. Don't worry, you're not responsible for understanding all of these integrals, but let's just look at one of these. So this is a sample of some data that you might have for such a tower. The blue curve is the equilibrium data. This is what you might develop from, say, thermodynamics, or you've measured this, you found a data table in the literature. So that's the equilibrium curve for a system. Now, my axes here, it's the x-axis and the y-axis, but x is the liquid phase composition and y is the vapor phase composition. The green line is the operating line. Now, the operating line describes the composition of the liquid and vapor at the top of the tower and the bottom of the tower, connected with a straight line. And what we want is in between the feed and the exit for the tower, we expect things to be connected linearly. There will be a smooth transition. Now, in order to do these formulas, we need to know, for some of them, the interface composition. So, I'm going to just have to say for this one, trust me that this is correct what I'm telling you here. But if you look at a material balance, a line drawn from each point on and that's not red, it's a green line, with a slope of negative kx over ky, and that's about how the mass transfer happens, it's going to intersect the blue curve at the equilibrium or interface point. So if I were to draw a line with a slope of negative kx over ky, then this point here where it intersects is going to be xi, yi. And I could do that for that same slope at a variety of points, and these would be a set of xi, yi's along here. Now the point at the top, this is going to be an xy point. Okay, so for particular x and y, there's an xi, yi that's determined for that based on a line with slope negative kx over ky. Now that then we apply the formula for the integral, and we can apply trapezoid rule or Simpson's rule and do a calculation and determine the size of a tower. And when I teach a mass transfer or separations course, I have the students do this. So we're going to, without deriving this, we're going to do just a sample calculation. Now my graph here is not the same as the one that you'll get when you download your worksheet, but let's just I'm going to do just a couple of points. What I want you to do is take a slope of negative kx over ky is equal to negative 1 over 2. So that means a rise of negative 1 and a run of 2. So that means my point is going to be, I can draw a straight line. Okay, more or less. I don't think I did a very good job of drawing it, but we have the straight line there. And I could do this for all of the various points. And because I'm lazy, I'm going to do just 3 points. Now what I want you to do is do this for at least 10 points. Okay? Now, you will eventually be doing these calculations using the trapezoid rule and Simpson's rule. So therefore, you need to make sure that you have an even number of intervals, so an odd number of points. Okay? And then I want you to then use this to estimate the values of y. So this is y1, this is yi1. At my next point, this is y2. This is yi2. y3. yi3. Now you'll be doing many more points than this. Okay, minimum of 10. And remember, you're going to be doing this for the trapezoid rule and the Simpsons rule. Now, when you do this, so then it's just a matter of reading the scale, okay, and find out the y value for these two. And your function, function of y is 1 over y minus yi. So you want to record, I usually do a y column and a yi column, and then evaluate the function. So in this first case, y looks like it's 0.05, and yi is, we'll just go with 0.04. And so this is 1 over 0.01, so this is equal to 10. All right, and I'm going to do this for each of my various points. So I'll get entries for each of these things here. And then I want to take the integral of f of y dy, where f of y is this column here, 1 over y minus yi. You'll do that with both trapezoid rule and Simpson's rule. And there's a handout that you'll get in Canvas. So that concludes this explanation. I will do a little bit of a second run at a hands-on with this in another video. Thank you very much for your time.